All right, so we are going to be talking about more about vectors, but in this case, we're talking about some applications of vectors and vector addition. Um, One of the key concepts in this area is equilibrium, and we've kind of been talking about situations that are at equilibrium. We just haven't been calling them that, because whenever something has no net force acting on it, it's at equilibrium. Even if it's moving, it can still be at equilibrium if there's no net force acting on it. If it's moving with a constant velocity, there's no net force acting on it, and it's at equilibrium. So we have we've been talking about calculating the resultants of forces acting on an object, and if those forces acting on an object create a net force, a resultant net force, then you can figure out what's called the equilibrant force, which is a single force that, when added to that situation, would cause equilibrium, would bring it back to a net force of 0. So really all you got to do is figure out to find the equilibrant force. You just have to figure out what the resultant of the other forces is and apply a single force that's equal in magnitude to the resultant, but exactly opposite in direction. So the equilibrant force is equal in magnitude, size, and opposite in direction to the resultant of the other forces acting on the object. Here's a couple example problems. Again, we'll work these in class, but I'm going to go ahead and kind of show you how that works with the diagram. So two forces act on an object. One is 6 newtons horizontal, the other is 8 newtons vertical. What single force will bring the object into equilibrium? So you would draw your coordinate plane. And you have a 6 Newton force horizontally, and we'll say this. We'll draw it this direction because it doesn't say negative 6 newtons, so we'll have it pointing in the positive direction there. And then we have an 8 Newton force vertically. Again, we'll draw it straight up because it says positive 8. So this is 6 newtons. This is 8 newtons. Now the resultant force would be right here at this angle. So the equilibrant force is going to be equal in magnitude but opposite in direction to that resultant. Call that FEQ. Basically, all you got to do is find out what the resultant force is and what the angle it is heading in, and add 180 degrees to the angle. So, again, we will actually do the math in class to finish working this problem, but I just wanted to kind of use a diagram to give you an idea of what we're talking about with the equilibrant force. Equal in size, opposite in direction to the resultant. Oh, in this unit where we're kind of taking these ideas of vectors and applying them, we also get into situations where things are sitting on an inclined plane, a ramp. And when things are sitting on an inclined plane, that kind of changes the way we have to look at them, because the surface that it's sitting on is no longer horizontal. But the weight of the object still acts straight downward toward the earth. So when an object is sitting on an inclined plane, its weight is at an angle to the surface that it's sitting on. And so it can be broken down into two components, parallel and perpendicular component. So one of the forces, one of the components of the object's weight acts parallel to the inclined plane. The other one is perpendicular to the inclined plane. Real quick, show you how that looks. So this is the ground, and this is the inclined plane, and this is the object here. The object's weight is still going to act straight downward toward the earth. And I believe this is coming up in the notes, but I'm going to go ahead and talk about it right here. Since the object's weight acts straight downward, perpendicular to the ground, and part of its weight acts perpendicular to the surface of the inclined plane, we call that F perpendicular. It's pretty clever. Part of its weight acts parallel to the inclined plane. We call that F parallel. We can take the parallel component and move it down here to close off this right triangle. And although for now I'm just going to go ahead and take that and put it back so that I can point out that since the weight is perpendicular to the ground, and the perpendicular component is, well, perpendicular to the surface of the inclined plane. Using our skills of geometry, that tells us that this angle in here is the exact same as the angle that the ramp makes with the ground. So a problem will tell you an object is sitting on an inclined plane that has an angle of however many degrees. Whatever angle the inclined plane has, the angle between the perpendicular component of the weight and the weight itself is the exact same. That's what this is talking about right here. And once again, I've forgotten to change this slide. So instead of a W here, we're using FG. So because the perpendicular component is perpendicular to the inclined plane and the weight is perpendicular to the ground, you have a similar triangle being formed by the weight, the perpendicular component, and the parallel component. Because of that, that angle formed by the perpendicular component and the weight, oops, wrong one, FG, is the same as the angle of the inclined plane. And so, to find the parallel component of the object's weight, the parallel component, if you go back and pay attention to how I closed that triangle off, the parallel component would be the opposite side to that angle. So you would take the hypotenuse, which is the object's weight, times the sine of the angle. Perpendicular component would be the adjacent side to that angle. So you'd take the object's weight, which again is the hypotenuse, times the cosine of the angle. And that gives us the parallel and perpendicular components. Now, I want to point out at this time that normal, again in physics, means perpendicular to the surface. So this is where, before when objects were sitting on a horizontal surface, like this, the normal force was equal to the weight. Almost with the same symbol again. Well, now the object's not sitting on a horizontal surface, and normal means perpendicular to the surface. So now the normal force, when an object is sitting on an inclined plane, the normal force is equal to the perpendicular component of the object's weight. So we'll go ahead and save the problems for class time. So we got to look at two situations. An object can be sliding down an inclined plane, and in that case, the force that's acting down the inclined plane is the parallel component of the object's weight. That's the force that causes it to accelerate down the plane. Or, if it's just equal to the force of friction, it'll slide down the plane with a constant velocity. So, net force, the force that causes acceleration for an object on an inclined plane, would be equal to the parallel component of the object's weight plus the force of friction. Now, don't forget, force of friction is equal to the coefficient times the normal force. That's an ugly move. Coefficient times the normal force. And on an inclined plane, normal force is equal to the perpendicular component of the object's weight. When an object is sliding down the plane, friction always opposes motion, so friction is acting up the inclined plane. On the other hand, if an object is being pulled up an inclined plane, well, the parallel component of its weight is still acting down the inclined plane. It's kind of like when you pick an object up vertically, the applied force upward is being worked against by the object's weight downward. But when you pull an object up an inclined plane, your applied force is going to be going up the plane. You're pulling or pushing. The parallel component of its weight is still acting down the inclined plane. And friction always opposes motion, so if you're pushing the object up the inclined plane, friction is also going to be acting down the inclined plane. So, in that case, net force is equal to your applied force plus the sum of the friction force and the parallel component of the object's weight, which would both have to be considered negative in this case because they are working in the opposite direction of your applied force. And once again, force of friction is equal to mu times Fn, and Fn is equal to the perpendicular component of the object's weight. We'll talk about that in class. We'll do the example problem in class. And lastly, we're talking about friction on an inclined plane. Now, mu s, when we put a little s under it, that's talking about static friction, how much friction there is before the object starts to move. There's another W I need to change to FG. And here's another one. And this one. There's one. All right. So, static friction, again, is the friction that we need to overcome when something is not moving. And at that point, when static friction is just overcome, then the parallel component of the object's weight is equal to the force of friction. So if we replace these two things with the equations to find them, to calculate them, F parallel is equal to Fg times the sine of the angle, and Ff is equal to mu times Fn. Now, Fn is equal to Fg times the cosine of the angle. So, we can substitute that in to this part of the equation for Fn, and we'd have Fg times the sine of the angle is equal to mu times Fg times the cosine of the angle. Now, since weight is on both sides, if you want to find mu in this case, you would divide both sides by Fg times the cosine of the angle. I'll show you the step that I cut out here. And you would have Fg times the sine of the angle over Fg times the cosine of the angle. Well, Fg is the same, so it cancels itself out. So what you're left with is mu is equal to the sine of the angle divided by the cosine of the angle. And if you remember your geometry, trigonometry, sine divided by cosine is equal to tangent. So, if you lift a surface, like you've got a board laying flat on a table and an object sitting on top of the board, if you start to lift one end of that board up and find the angle that the object just starts to slide at, the tangent of that angle would be equal to the coefficient of friction. All right. So hopefully this helps give you a good idea of how we're going to be taking these concepts of vectors, vector addition, vector resolution, and applying them to situations of equilibrium and objects on an inclined plane. See you in class.